All right, we're moving into section 6.5. We're looking at graphing polynomial functions by hand now. And we're going to do this based on some of the observations we made from our previous lesson, okay? One thing we talked about last lesson is end behavior, so I've got a quick review of it on your screen right now. We know end behavior is based on the degree of our function being even or odd, as well as the sign of the leading coefficient being positive or negative. So I have that all written out already here as a quick review. You can reference this at any time as we work through our examples, okay? Now, one new concept we want to talk about before we start graphing ourselves is that of multiplicity. The number of times a zero is repeated in our function is said to be the multiplicity of the zero. All right, and remember, zeros are just x-intercepts or roots of the function. Okay, so how many times that repeats is your multiplicity. And this is important because the multiplicity has a direct effect on the graph of the function at each one of those zeros. Okay, so let's illustrate this. All right, so here we have a function p of x, and it's given in its factored form, x plus 2 times x minus 1 times x minus 3. The reason we have the factored form is it helps us see the zeros of the function very easily. The factors correspond to zeros of -2, +1, and +3, right? Now notice each one of those factors in the equation for p of x, they're being raised to the first power. And that power is what tells you the multiplicity of the corresponding zero. So right now, all three of these zeros have a multiplicity of 1. And notice the behavior of the graph at each one of those zeros. Right now, the curve is crossing through one side of the x-axis to the other side of the x-axis as it passes each one of those zeros, okay? Now, let's just focus on the multiplicity for the zero of -2, okay? Which means I'm going to play around with the power of the corresponding factor, x plus 2. So let's change it so that the power on x plus 2 is 2, okay? Notice how that affects the behavior of the curve at x equals -2. Now that the multiplicity is 2, the curve is touching and turning right back around at -2. Okay. What if I change the multiplicity to being 3? Okay, so now we're back to the curve crossing through at x equals -2 from one side of the x-axis to the other side, kind of like it did when the multiplicity was 1. However, see, now there's a little bit of a bend to the curve as it crosses through at x equals -2. Let's increase the multiplicity to 4. Now we're back to at x equals -2, touching and turning right back around. But notice we're a little bit flatter at x equals -2 versus back here when the multiplicity was 2. We're not quite as flat. Okay. If the multiplicity is 5, we are back to crossing through, yet we're still flatter yet than we were back when the multiplicity was 3, let's say. Okay. And then when the multiplicity is 6, we're turning right back around, similar to what we did when we were at 4 or 2. Okay. So the multiplicity can be generalized based on whether it's an even number or an odd number and how that affects the curve. All right, so let's put this in our notes. So let's say that r is a zero of even multiplicity in our function. Then that means the graph of the function will, we're going to say, touch the x-axis at r. All right, so here's what I mean by that, by the word touch. Okay, so if right here is the zero of r, then your curve will, as it gets to r, it's going to touch it and turn back around rather than crossing through the x-axis. Okay. Sometimes students, instead of referring to this as touching the x-axis, they say that it's bouncing. Okay. Now, if r is a zero of odd multiplicity in the function, we've seen that the graph of f of x will cross the x-axis at r. So what I mean by that, if right here is r, then the curve is going to have to cross through to the other side of the x-axis. Okay. All right, so moving forward into some examples here. At the top, I have both the graph of a function as well as its equation, okay? And we're going to identify the intercepts of the function as well as the end behavior, okay? So your y-intercept, you can reason out one of two ways. You can look at the graph, and I can see that it's at 8, so y equals 8. Or you could have used the equation and evaluated it at x equals 0. That should also have given you 8. Okay. Now x-intercepts, again, you can look at the equation or the graph. If you're looking at the equation, the x-intercepts come from your factors, okay? So x plus 2 leads you to an x-intercept of -2. And notice how that factor is being squared. So that tells me there's a multiplicity of 2. So if you're looking at the graph, see how at x equals -2, you're touching and turning right back around. Your other x-intercept is at 1. That comes from this factor. It's being raised to the first power, so the multiplicity here is 1, and that's why at equals 1, you're just crossing through to the other side of the x-axis. Okay. Now, end behavior is going to be based on the sign of the leading coefficient as well as the degree of the function. I can tell it really easily just by looking at the graph, though. It's up on the left, down on the right, meaning as x approaches infinity, f of x is approaching -infinity, and as x approaches -infinity, f of x is approaching infinity. Okay. All right, second example here, all we're given is the graph of the function, and now we need to write the equation for the function from that graph, okay? So starting with the y-intercept, it's got a y-intercept at -2. It looks like it has an x-intercept at -2. And I would say the multiplicity on that appears to just be 1 since we're crossing through to the other side of the x-axis. I have another x-intercept at 1 right here, and for that I would say the multiplicity is most likely 3. That's because while we're crossing through to the other side of the x-axis, you see there's a little bend in the curve, okay? And then end behavior is up on both ends, meaning we're approaching positive infinity on both ends, okay? So taking this all into account, I can build the function f of x for this graph first by using my x-intercepts, okay? My x-intercept of -2 means that x plus 2 should be a factor of the function, and it should have a power of 1 on it. My x-intercept of 1 means x minus 1 should be a factor, and it should have a power of 3 on it, okay? And notice if you add the powers up on those factors of 1 and 3, you get a total of 4, which means the degree of this function is 4, and that matches the fact that the end behavior is heading in the same direction on both ends, okay? Now, we have to verify that this function has the y-intercept of -2. To do that, just evaluate it with 0 for x. So that would be 2 times -1 to the third power, which of course is -2. Had the function not had the proper y-intercept, then you would just have to play around with a coefficient that you put out in front here in order to match that y-intercept. So what I mean by that is, let's say instead of at -2, the y-intercept right here, let's say that was -4, okay? then in order for this function to have a y-intercept of -4, you would need to put a 2 out in front here, so that this would become 2 times -1 to the third, which would give you -4. Okay. All right, moving forward. So now we're given the equation of a function, and we're going in the other direction. Now we're sketching the graph from that equation. I need to identify several pieces of information in order to sketch this curve. So starting with the y-intercept, I can find that using the function if I evaluated it 0. So that would be the negative of -3 times 2 times 1, which is +6. We plot a point on the y-axis at 6. X-intercepts are going to come off of your factors. So the first x-intercept will be 3 off of this factor. It has a multiplicity of 1. Okay. Next intercept would be x equals -2 off of this factor. It also has a multiplicity of 1, right? Because these powers on the factors are 1. And then let's plot that. And then my last x-intercept will be -1, also with a multiplicity of 1. All right, now to find the degree of the function, simply add up all of your multiplicities. I have a multiplicity of 1 3 times, so the degree here is 3. And that's an odd number, okay? Sign of the leading coefficient, don't overcomplicate this. See that negative out in front of all the factors? That means your leading coefficient is going to be negative, okay? Now, degree and leading coefficient help you determine your end behavior. For an odd degree function with a negative leading coefficient, your end behavior should be up on the left and down on the right, okay? Meaning as x approaches negative or positive infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches positive infinity, okay? All right, now we've got plenty of information that we can draw a reasonable sketch for this curve, okay? We know we're supposed to start high on the left, finish low on the right, and because all of these x-intercepts have a multiplicity of 1, we should be crossing through each of the x-intercepts like a line. So the curve's going to be doing something like this, most likely. Okay. Now here's what's in question. Where these relative extrema are, the relative maximums and minimums, these are in question. We can't determine their exact locations until we learn some calculus, okay? So for now, we're just concerned with knowing that there has to be a turn in between x equals -2 and x equals -1, as well as a turn in between x equals -1 and +3, okay? So I'm not super concerned with where those turns take place, just as long as we know that they have to actually happen, okay? Let's do one more example. All right, here's our function. Y-intercept here, f of 0 would be 0 times -2 squared times 3. That's just going to be 0. Your first x-intercept is going to come off the factor of x. It's x equals 0. That's being raised to the first power, so it has a multiplicity of 1. Your next x-intercept would be at 2. That's off of this factor. It has a multiplicity of 2. And then final x-intercept would be off of this factor, x equals -3. Its power is 1, so multiplicity 1 here. Add all your multiplicities up to give you your degree. That's 4, which is even. And then your leading coefficient here is positive. Okay, so that's going to make your end behavior up, even degreed function with positive leading coefficient. So we're heading in the positive direction on both ends. Okay. All right, so now plot what we know. I didn't put my other x-intercepts on here. Okay, so those are the only 3 points I have to work with here, along with my in behavior. And I'd say the big thing to not overlook is the fact that x equals 2, its multiplicity is 2. So that tells me that when I get to x equals 2, I should be touching and turning right back around with that multiplicity being even. Okay, in behavior says I start high on the left, I finish high on the right. So curve's going to do something like this. It's going to have to cross through at -3, turn around, cross through at 0, turn around, hit 2, immediately turn back around to finish high. All right, once again, these turns, the relative extrema, are unknown exactly where they should be. Okay. All right, your turn to practice. Pause the video, try the next problem yourself, and then when you're done, come back and check your work with mine.